Hello students, welcome to a live session with Time. We are going to have a session on chemistry, a chapter from chemistry, which is there in the 12th syllabus for both state and CBSE. And the chapter is welcome to a live session with, and the chapter is solutions. Now, in this solutions chapter, what are all the things that we will be going through? Because this is a session of about 1 hour. So let us check what all things we can do. Now, before we get into the things like what we are going to do, let us check what is a solution. A solution is a homogeneous mixture. Homogeneous mixture means it's a uniform composition mixture. Means let us say that you have a sugar dissolved in water. You have dissolved it in such a way that there are no sugar crystals seen. You drink any part of this water, it will be equally sweet, right? Take the first drop or the second drop with a spoon, right? The sweetness is the same. So it is a uniform composition. Means it's a homogeneous mixture of two or more substances. So solution is a mixture, but it is a homogeneous mixture. Unlike what we find between sugar and salt mixed together in the solid, both are powder, right? But still, if you take any part of that particular powdered mixture, you will not have the same salty or the sweet nature. So we find that sugar and salt in the solid, they do not make a homogeneous mixture. So they are heterogeneous. Next, if you take up a binary solution is where you have only two components. And the one which is in greater quantity is called the solvent. And the one which is in lesser quantity is the solute. Now, there is one very important thing that we need to know. Suppose you have taken a sugar syrup. A sugar syrup is in what physical state? It is in liquid. Sugar syrup is made up of what? Sugar, which is solid, and water, which is liquid. Now, sugar syrup is also a liquid. You'll be surprised to find that the sugar part is only about, or the water part is only about 40%, right? Sugar is 60%. Still, it is having the same physical state as water. So water becomes a solvent. So in this case, you find that though water is to a lesser extent, the physical state of water is matching with the physical state of the solution. And that is how water, though it is lesser in quantity than the solute, which is sugar, it is having water as a solvent. So this part is to be taken up, right, seriously here. The component which is in the same physical state as a solution, right, that is considered as a solvent. Though we have taken this, we have considered this, there are exceptions to that, right? And the most important thing is this, that the solvent's physical state and the solution's physical state must match. I hope this is clear. So shall we move on further? All right. So if there are no questions, we'll move on. Here, we have got some 9 combinations of solutions. It may be a gas in a gas, which is having gas as the final state, right? So let me make it more clearer. So a gas in a gas, right? Example is air. A liquid in a gas is, you can take chloroform, which is a liquid, which is in contact with nitrogen gas. Or a solid in a gas, camphor is a solid, and the gas is nitrogen. So we have gaseous form, solid form, liquid form of the final state, right? And then let us look at this alloys. Alloys are solid plus solid combination, right? Aerated drinks are gas in liquid. For example, carbon dioxide dissolved in water. So like that, we have got various combinations here. 9 of them we have seen here. So I hope these are all known to us, right? We are familiar with all these different kinds of solution in whatever physical state they are, whether they are gases or solids or liquids. Hope this is clear. So now, which is what we started with, what does this chapter contain? What is this chapter? This chapter is solutions. And you know that solutions forms part of your 12th chemistry chapter, right, under physical chemistry. What does this contain? The first thing is discussion of a gas dissolved in liquid, which is governed by the Henry's law. Next, we have got liquid volatile solute dissolved in liquid volatile solvent, and this is governed by the Raoult's law. And then we have got a non-volatile solute. So this was a volatile solute. This is a non-volatile solute dissolved in a volatile solvent, and here we read colligative properties, right? I hope this is clear. So these are all the 3 parts that we have under the solutions. I hope you all know what are the concentration terms, right? For example, molarity, molality, normality. We have got a mole fraction. We have got a weight fraction, weight percentage, ppm. All these things are concentration terms, right? The strength of solutions are expressed in terms of all these things, right? So this part, I know that this is being covered in the 11th standard itself, right? And you're familiar with all these things. So this chapter is going to take up 1, 2, and 3. Probably in the time that we have today, we'll be discussing probably only the first one. If time permits, we'll move on to also the second one. We'll probably do some questions based on this Henry's law. So we are going to take up gas dissolved in liquid. If you have any doubts, you can ask, right? You can put it in the chat box. I'll answer your questions. Now, so far I have not seen any questions here, but at the same time, I expect questions to come and give me an opportunity to answer your questions. Thank you. Now, when we talked about solutions, we talked about binary solutions, isn't it? We said there is a binary solution. A binary solution has got only 2 components. Let us say 1 and 2, right? One could be the solute, the other could be the solvent. Now, in this binary solution, we said that we can deal with a gas dissolved in a liquid. So one of these components is a gas, the other component is a liquid, and the gas is dissolved in this liquid. For example, you have all these soft drinks, right? Soft drinks have got the gas carbon dioxide dissolved in water. Similarly, all water that is above the ground, right, has got oxygen dissolved in it, and this dissolved oxygen is the one that is feeding all these aquatic plants and animals, right? So oxygen that is dissolved in water is a dissolved oxygen. Dissolved oxygen is the one that is responsible for the respiration of all aquatic life, right? So this water is also like a gas in water, oxygen gas dissolved in water. So that is also of this type, gas in liquid. Now, before we move on to the Henry's law, there is something that we need to learn first. What is solubility? Solubility is the maximum amount of a substance. That substance is nothing but you can call it as a solute. Solubility of a solute, maximum amount. What is the maximum amount of this solute that can be dissolved in a specified amount of solvent? Specified amount means, let us say 100 ml, right? of the solvent. At a given temperature, the temperature also has to be specified because solubility depends also on temperature. So solubility is the maximum amount that can get into the solvent. Maximum amount of the solute that can get into the solvent of a fixed volume or a fixed mass at a particular temperature, right? So if you change this, the amount of solvent, the amount of solute that is going to get into it is also going to change. Similarly, you change the temperature and the solubility is also going to change. Now, what are the factors that affect solubility? First is the nature of solute and solvent. We know that benzene can dissolve naphthalene. Naphthalene balls we have seen, right? Or instead of benzene, let us use kerosene, right, which is available at home. So naphthalene can dissolve in kerosene. But the same naphthalene, can it dissolve in water? No, it doesn't happen. So there is solvent and solute, right? Compatibility. They need to be compatible. So naphthalene is basically non-polar. And the non-polar will dissolve in a non-polar, which is how we say like dissolves like. Means a non-polar solute will dissolve in a non-polar solvent. Whereas a polar water cannot dissolve naphthalene. A polar water can dissolve sodium chloride. The same sodium chloride cannot get into kerosene, but can get into water because non-polar and non-polar will match, polar and polar will match. So NaCl dissolves in water, right, but doesn't dissolve in kerosene. So that compatibility is there. Like dissolves like. I hope this is clear. Next, temperature. That is what we mentioned about. There are some substances which dissolve more when the temperature is lower. There are many which have greater solubility at a higher temperature, right? So temperature coefficient of solubility, right, decides whether the substance is going to be more soluble or less soluble at a lesser temperature. For example, if it is an exothermic solubility, exothermic means what? Giving out heat. So when A dissolves in B, right, there is loss of heat, means it is exothermic. What will happen? The solubility will become greater, right, when the temperature is lower. Whereas if it is endothermic solubility, the reverse happens. Clear? Then we have third factor, pressure. Especially for gas in liquid, not liquid in liquid. Keep this in mind. Pressure has more effect, right, when it is gas in liquid, because liquid in liquid or solid in liquid, they are not affected by pressure because liquids and solids are already condensed phases. They're already condensed. They cannot be condensed. Whereas a gas can be condensed. So by putting pressure, by applying pressure, a gas can be condensed, whereas a liquid or a solid are already condensed. Therefore, they will not have much effect of pressure on their solubility. So pressure's effect is mostly on a gas in liquid. The solubility of a gas in liquid is affected by pressure, not liquid in liquid, not solid in liquid. I hope this is clear. Yes. So let me give you some time to check whether you have understood, right? Whether you have any questions to ask, right? All these things can happen. So I'll give you small gaps in between so that you can come up with your doubts and then get them clarified before we take up the remaining part. All right. So far, so good. Solubility we have seen. What is solubility? And then what are the factors that affect solubility? I hope with this, we'll be able to move on further to this Henry's law. What is this Henry's law? We said that Henry's law is going to govern the solubility of a gas in liquid. Now, what is this law saying? The amount of a gas that is dissolved in a given volume of a given liquid, right, at a given temperature is directly proportional to the pressure of the gas. More the pressure, more the solubility of the gas in a given volume of a liquid at a particular temperature. So if you have seen soft drinks, you know that carbon dioxide at a high pressure is being dissolved into the liquid, right? And the lid sees to it that the pressure is maintained. The moment the lid is removed, all the gas comes out. So the gas was more dissolved only because the pressure was more, is it not? So at a higher pressure, the gas dissolved more. But when you lower the pressure, when you open the lid, you're exposing the entire liquid to atmospheric pressure, which is more or less close to 1 atmosphere, probably even less than 1 atmosphere, right? Then what all pressure that was present in the bottle, right, is being brought down to this. So when the high pressure present in the bottle and that could dissolve the gas in liquid was brought down to the atmospheric pressure by opening the lid, the entire gas comes out. So in no amount of time, you'll find that there is no carbon dioxide present in that water. Clear? So more the pressure, more the solubility. And if you lower the pressure, the solubility is going to become less. I hope this is clear. So this is a very, very simple law, right? Later you'll find that Henry's law, Raoult's law that you're going to read are actually extensions of the Dalton's law. Dalton's law was for gas in gas, which I forgot to mention there. Henry's law is for gas in liquid. Raoult's law is for liquid in liquid, whereas Dalton's law is for gas in gas, right? The gas and gas mixture was first treated by Dalton, was first studied by Dalton. So Dalton's law was pertaining to what? A gas dissolved in a gas. Now this is what? Gas dissolved in a liquid. It's an extension of the Dalton's law. Now how can we express this? The concentration is proportional to the pressure. Here, the concentration of the gas is in, you can take it in units of gram per unit volume, right? And P is the pressure. If you have a dilute solution, then we can replace that concentration with mole fraction. So we can write here that pressure and the mole fraction are proportional to each other. Our pressure is equal to the proportionality constant Kh, which is called the Henry's law constant, into X of the solute, that is mole fraction of the solute. Now we put P equals Kh into X, X of the solute. This X has got no unit, it's mole fraction. So whatever is a unit of pressure, that will become the unit of Kh. So Kh will have the units of pressure. Kindly note. So Kh will have the unit of pressure. So Kh is called the Henry's law constant. One more thing that you will identify here is that at a particular pressure, there is a particular solubility, right? Suppose I have carbon dioxide gas at a pressure of, let us say, 200 or 200 atmospheres, let us say, right? And we want to find out the mole fraction of carbon dioxide. Now I'll replace the CO2 with some N2 at same 200 atmospheres or lesser pressure. What will be the X of N2? Will it be same? I have maintained the pressure for both the gases. Can I get the same solubility? No, because each gas has got a particular value of Kh. The proportionality constant is not the same for all the gases. So shall we say that if Kh is less, the solubility is more for a constant pressure? Is it not? If this is less, it means that the solubility is more. So shall we say that a gas having lesser Henry's law constant has got more solubility at a given pressure. Clear? That is what we find out now, that lesser the KH value, more the solubility. This part will check here. Now, this is the Henry's law for a gas HCl, right? HCl is a gas. That HCl gas is dissolved in what? Cyclohexane. Cyclohexane is an organic solvent, right? And this is the partial pressure of HCl. As the pressure rises, the solubility also rises, the mole fraction also rises. This is what is a Henry's law in the form that has been shown there. Let us look at that part once again. P equals KH into X. Is this not like Y is equal to mx, which is a straight line passing through the origin? Yes. This is a straight line passing through the origin. And this m is the KH value, which is the slope. So the slope gives us the KH value. The slope will not be the same for all gases. Means the KH value will not be the same for all gases. So that is what we find here, that plotting pressure, partial pressure of that particular gas on the y-axis and the mole fraction of the same gas on the x-axis, we get a straight line passing through origin with a slope equal to KH. I hope this is clear. Yes. Now, different gases, that is what we talked about. Different gases will have different KH values at the same temperature. So KH is a function of the nature of the gas. We said carbon dioxide and nitrogen will not have the same KH value. They'll have different values. That is why at a particular pressure, the solubility of CO2 and the solubility of N2 is not the same. For the same volume of water, let us say, it is not the same because their KH values are different. So higher the value of KH, we put the reverse actually. We said lower the value of KH, higher the solubility. Now we are saying higher the value of KH, lower the solubility of the gas in the given liquid. I hope this is clear. Yes. Next, this law is obeyed closely at low pressure. Very important. So there is a limitation of this Henry's law. Henry's law cannot be applied at all pressures. Only at low pressure, this is more closely obeyed. Next, this law, just like the Dalton's law, is not applicable for gases which react with each other. No. There is gases which react with the solvent. So in Dalton's law, we say gas and gas, if they interact chemically, you cannot apply the law. Dalton's law is not applicable for gases which interact with each other. In a similar way, this Henry's law is not applicable if the gas is going to react with the solvent, which is a liquid, right? For example, if you take NH3 dissolved in water, it is going to react with water to form ammonium hydroxide. And that ammonium hydroxide is breaking into what? NH4 plus and OH minus ions. So there is a chemical change. So there is a reaction between NH3 and water. So Henry's law is not applicable for the gas ammonia dissolved in liquid water, right? So it's an extension of the Dalton's law, we said. So in Dalton's law also a similar condition exists, that the gases which are dissolving in each other must not react. So if there is a reaction, there is no longer this law valid. I hope this is clear. So even for Raoult's law, for that matter, you cannot have substances which are reacting with each other. So Raoult's law, we said, is liquid in liquid. Dalton's law, gas in gas. Henry's law, gas in liquid. Any of these combinations, you cannot have a chemical reaction occurring. Clear? Now, what are the applications of this Henry's law? So time for checking whether people have asked questions, right? So applications of Henry's law. The first application is, as we said, soft drinks or soda water, simply. So soda water, even the soda water that is supplied on the streets, right? They have this gas, right, bubbled at a high pressure into a bottle, right? And the bottle is now having carbon dioxide, and then they'll add whatever flavor you have, right? Lemon or whatever it is, and then make it palatable. So solubility of the CO2, right, is greater only when the bottle is sealed under high pressure, right? So when the bottle is sealed under high pressure, the solubility is going to increase. I hope this is clear. This everybody knows, right? And when the lid is removed, the gas is gone. Now, this is very, very important. Deep sea diving. The scuba divers carry cylinders which are filled with air diluted with helium. Previously, they used to take nitrogen, and then they faced a very dangerous situation, which we'll talk about. This is in order to reduce the painful effects of bends caused by the release of nitrogen gas dissolved in blood when they come towards the surface. Now, we'll spend some time on this bends, right? How dangerous is this phenomenon called bends? Now, let us say that we are at the sea level. This is the sea level where the pressure is 1 atmosphere. Is it not? Pressure is 1 atmosphere at the sea level. As suppose a diver has gone down, right, deep into the sea. As you get into the depths of the ocean, the pressure becomes much greater than 1 atmosphere, right? The diver has got oxygen, right, to breathe in, and the diluent of oxygen is nitrogen, because we cannot breathe oxygen pure. Pure oxygen will make the heart beat to death, right? You cannot have oxygen supplied at such a high concentration, right? So you need a diluent here. So nitrogen is the commonly available diluent already present in natural air. So nitrogen is to the extent of more than about 78%, and oxygen is close to 20%, right? Remaining are all other gases, including water vapor. Now this is a diluent. So when the cylinder had this combination of oxygen and nitrogen, nitrogen being more, oxygen less, and the diver was getting deep inside, right? These gases got into the solvent of the human, that is blood. So as the oxygen and nitrogen are being taken up, right, they enter into the blood more because the pressure is more, because P equals KH into X, right? Oxygen has got a KH, nitrogen has got a KH. Proportionately, the solubility of nitrogen and oxygen will be there in the blood at a pressure which is rising as the diver gets into the depths of the ocean, right? So oxygen and nitrogen have got into the blood more. Oxygen has got a role to play. Oxygen gets metabolized. In fact, all the cells require nitrogen to breathe in. Oxygen to breathe in, because oxygen is the one that is going to supply what to all the cells, right? You know that hemoglobin carries the oxygen, and this blood has that hemoglobin, more oxygen, more into the cells, more oxygen is going to the cells. So oxygen is getting metabolized, but nitrogen is a spectator. Nitrogen has got no role to play, but still it has gone into the blood because of this factor, Henry's law. But suppose, let us say that the diver has to return to the surface immediately because there is some danger there down, right? He has seen, he has noticed that there is a danger. Let us say that a shark is coming, shark is on its way towards the diver. So diver has to go up sharply, right, in less time. So as the diver rushes up, the nitrogen and oxygen also rush out, but oxygen is already metabolized. So it is a nitrogen part which is getting out of the blood at such a pace that the diver is unable to take it. The entire body bends in pain. That is why the phenomenon is called bends. This bends is because nitrogen is rushing out of the blood, right? Because the diver is rushing towards the surface, the pressure is also getting lowered from such a high pressure to such a low pressure. The nitrogen comes out of the blood, right, and causes bends. This is what is bends. So then they found that let us replace this nitrogen with helium, because helium has got more KH value. More the KH value, less the solubility. So when He has got lesser solubility, it has gone less into the blood at high pressure, therefore will not come out of the blood so much, right, rushing in order to cause bends. Therefore, nitrogen has been replaced by helium, which is what you saw here, right, in the previous slide, that it is diluted with helium, not with nitrogen gas, because nitrogen gas causes bends, because nitrogen is more soluble than helium. Nitrogen has got lesser KH value than helium, and therefore dissolves more in blood, and therefore causes more pain, right? So the scuba diving is now having helium instead of nitrogen to dilute the oxygen. I hope this is clear. Yes, so much of practical importance is this Henry's law. Now the third application is, we said that this was a sea level and the diver is going down. What if we go up to a higher altitude? The oxygen partial pressure is less. So the oxygen entering the blood will become less. So O2 in blood is lowered as we are going up, higher up, right? So sometimes what happens, because of the deficiency of oxygen, the person, right, feels weak. The thinking, what shall we say, abilities will come down, and this condition is called anoxia. Means anox means less oxygen, deprived of oxygen. So that condition is called anoxia. So both the things we have seen, increase of pressure and then decrease of pressure, right? So as you go up, the oxygen is becoming lesser in the air, and therefore the blood will receive less oxygen, and therefore we reach a condition called anoxia. Whereas deep down we have high pressures and we have got this bends, right? So these are all the applications of Henry's law. Henry's law, we said, is for gases dissolving in liquids, the gases which have not chemically interacted with the liquid solvent. I hope this is clear. Yes. So shall we check if there is any question, right? So I hope things are clear enough, right? Not to the extent of getting doubts. Yes. All right then. So we'll now take up a few questions, 2 questions to be particular, to be specific, on Henry's law, based on Henry's law. The amount of carbon dioxide in grams that can be dissolved in 540 ml of water at 2 bar pressure is, KH for CO2 is given already, but that is in pascals. That we need to convert, right? You know that 1 bar equals 10 power 5 pascals. So we'll put the equation, P equals KH into X. What is X? Mole fraction of CO2. So number of moles of CO2 by number of moles of CO2 plus number of moles of the solvent. What is the solvent? Solvent is water, right? Then what he says, that the density of the solution is 1 gram per ml. We know that for these gases in liquids, the gases are so less. One more thing we said, that the solution is dilute. Only then the Henry's law is valid. So in a dilute solution, shall we say that the number of moles of CO2 will be much less when compared to number of moles of water. So the solution is as if it is pure water. So density of the solution is almost like density of water. If density of water is 1 gram per ml and we have got 540 ml of water, shall we say that we have got 540 grams of water? So weight of water, right? In chemistry, we do not distinguish between mass and weight. Though it is mass, we call weight. Molecular weight is molecular mass. no difference. So weight of water is 540 grams, right? Because the volume is 540 ml and the density is 1 gram per ml. So the solution's density and the density of water, they are almost the same. Why? Because there is so less gas in water. And you know that Henry's law is valid only for a dilute solution, is it not? So I'll replace or I'll ignore this NCO2 in the denominator. It is something like drop added to ocean. This is the ocean now because it is water, completely water based, right? How much is this pressure? The pressure is 2 bar. I'll put this bar as it is there. So let us put the numericals here. 2 bar equals KH. What is KH? 2 into 10 power 8 pascals. So, or I can also convert this bar into pascals. I think that will be better. So on the left hand side, I have got pascals. What was the number of bars? 2 bars. So 2 into 10 power 5 pascals. Right hand side is also pascal into number of moles of CO2 by number of moles of water. How do you get the number of moles of water? Weight by molecular weight, right? What is the weight? 540. What is the molecular weight of water? 18, right? This 2 and 2 will cancel out. So number of moles of CO2 equals, carefully look at that. This 10 power minus 8, when it go to the other side, it becomes 10 power minus 8. So 10 power 5 minus 8 is 10 power minus 3. Into, what is this? 540 by 18, 18 3s are 54. So into 30. So this is 3 into 10 power minus 2. This is moles. How to get the grams? Multiply the moles with the molar mass. So 3 into 10 power minus 2 multiplied by 44. So 44 3s are how much? 132. So 132 into 10 power minus 2 grams is 1.32 grams. So B is the answer. I hope you have followed this. So this is the key equation for us, the Henry's law. And then we said it is a dilute solution. And therefore we said the density of the solution and the density of water is the same. So water will have 540 grams because of that, because we have 540 ml of water. And 540 grams of water will give you how many moles of water? 540 divided by 18, right? And then we said that NCO2 is much small when compared to N of H2O, so that it can be ignored in the denominator, right? And that is how we got this as the grams of CO2 that are dissolved in 540 ml of water at 2 bar pressure. I hope this is clear. Yes. One more Henry's law question we'll take up. Now, Henry's law constant for the solubility of nitrogen gas is 70 kilobar. Kilobar means into 10 power 3. At 298 Kelvin, then the mass of nitrogen present in 1000 ml of water, right, packed under 2.5 bar. So pressure is how much? 2.5 bar. So P equals KH into number of moles of N2 by number of moles of N2 plus number of moles of water. Similar there, right? There we are taken up carbon dioxide and here we are taking nitrogen. Pressure is how much? 2.5 bar. So put that here, 2.5 equals KH 70 into 10 cube, which is in bar now. It was in kilobar given there, into number of moles of N2 by number of moles of N2 plus 1000 ml of water. 1000 ml is same as 1000 grams because you know that density of water is 1 gram per ml, right? So shall we say 1000 divided by 18, which is a molar mass of water? I'll ignore this number of moles of N2 like what we did in the previous session, in the previous question. So now this is 55.5. So number of moles of N2 equals 55.5 into 2.5 divided by 70 into 10 cube. Clear? Have we missed anything here? Nothing. All right. So this 2.5, can we not write this as 5 by 2? Yes. This is number of moles of nitrogen. We want the mass of nitrogen. What is the mass of nitrogen? That is the weight of nitrogen. I'll multiply with 28, which is a molar mass of nitrogen. Yes. Check what we have done. Yeah. Now, 14 goes in this, 14 tables, 14 twos are, 14 fives are. This 5, that 5, this 2, and that 2 have got cancelled out. So you've got only 55.5 into 10 power minus 3 grams. Or shall we say 5.55 into 10 power minus 2 grams? Yes. Option D it will be. Same formula. Same formula that we have employed in the previous question, right? Same formula that you have seen under the Henry's law. Yes. So we have tested our knowledge. Yes. Good enough. So we have done Henry's law. That is the first part of this chapter solutions we said. And fortunately, there is sufficient time for us to take up the second part, which is the Raoult's law, which is for liquid in liquid. I'll give you some time, a few seconds, to check if you have understood, right? Or if any questions are there under Henry's law, we'll clear them and then we'll move on to the second part of this chapter. So if we find that we are not able to complete this Raoult's law, right, we'll continue this in the next session. So with that thing in mind, we are continuing now. So the seconds that I have given are over, and now we'll be in a position to take up the second part of this, which is the Raoult's law. So what is Raoult's law? Raoult's law is for liquid in liquid. So it's a quantitative relationship between partial vapor pressure and the mole fraction of components in a solution, which is same as the Henry's law. Henry's law also is a relationship between P and X. This is also between P and X, right? But what P? It is a partial vapor pressure because it started with a liquid. So liquid will have a vapor pressure. Clear? There it was partial pressure of the gas itself because it was already a gas. But here the liquid has been converted into gas. So that is vapor pressure. Now, Raoult's law states that at a given temperature, Henry's law also is at a given temperature. For a solution of volatile liquids, both the liquids are volatile. We said liquid volatile solute plus liquid volatile solvent. The partial vapor pressure of each component is directly proportional to its mole fraction. Clear? So it's a very, very simple statement. The temperature is kept constant and the partial vapor pressure of each component, because both are volatile. So let us say A and B are the two liquids. A is the solvent. Usually A we keep as a solvent and B we take it as a solute, right? So A will also give a vapor pressure. B will also give a vapor pressure. That is why we are saying partial vapor pressure of each component is directly proportional to its mole fraction. Now, how do we express this? This is what is a partial pressure of component A, let us say solvent, and this is for the component B. This equation is very similar to the Dalton's law, which states that the total pressure is the sum of the partial pressures. Under the Dalton's law, the same idea has been borrowed from the Dalton's law and applied here for the Raoult's law. Dalton's we said was gas in gas, Raoult is for liquid in liquid. So pressure total is PA plus PB is exactly borrowed from the Dalton's law, right? Whereas these are what? Vapor pressures. Those are partial pressures of the gas. These are vapor pressures of the two liquids. How is each vapor pressure dependent on PA is proportional to XA, they say. That's what they said here, right? Partial vapor pressure is directly proportional to its mole fraction. That is what you are showing it here in this. That PA is proportional to XA, or PA is equal to PA naught into XA. What is this PA naught? PA naught is a vapor pressure of the liquid when the liquid is alone. What is PA? Vapor pressure where the liquid is in the presence of another liquid. So PA is the vapor pressure of the liquid in solution, and this is vapor pressure in pure liquid A. That is what you have added up here. PA, we have taken it as PA naught into XA. PB is PB naught into XB. Small mathematical thing we'll do here using this. You know that XA plus XB is equal to 1. Do you all know? Because the sum of mole fractions is equal to 1. Because the sum of all fractions is equal to 1. Is it not? There are only two substances, A and B, and you add up their fractions, it should be equal to 1, right? So we'll do a small trick here. Take the P total as P equals that XA, I'll put it as 1 minus XB, can be into PA naught plus XB into PB naught. Clear? So I can take this as PA naught plus XB into PB naught minus PA naught. Can we not? So we can take this equation by removing this XA, replacing it with 1 minus XB, and then simplifying that part and getting an equation of this kind, which is very similar to a y is equal to mx type of relationship. If this P is plotted on the y-axis and this XB is plotted on the x-axis. And what will be the slope? The slope will be PB naught minus PA naught. What will be the intercept? Intercept will be PA naught. This is clear? Yes. Even for those who are not from the mathematical background or mathematics background, those who are from the life sciences background, right? They will still find that these are all the equations that you've already covered even before they reached the 10th standard. So y is equal to C plus mx is a straight line, right? Not passing through origin. It will pass through origin when C is equal to 0. Y is equal to mx is a straight line passing through origin. So this is y is equal to C plus mx. So C is the intercept. What intercept? Y intercept. So C is a y intercept, right? And m is the slope, which is equal to PB naught minus PA naught. You can plot P versus XB and then get a straight line. So getting of straight line is, what shall we say, a verification of the Raoult's law. So if you get a straight line, it means that Raoult's law is verified. Means the two liquids have obeyed the Raoult's law. I hope this is clear. Now we'll move on to what is the composition of the vapor phase. You know that the composition of the vapor phase is given by the Dalton's law. How? Let us say that Ya and Yb are the mole fractions of A and B in the vapor phase. You know that Xa and Xb are the mole fractions in the liquid phase. So let us say that you have got a beaker having a combination of the two liquids A and B, right? Let us say that you have placed a lid, airtight lid. You know that molecules of A and B are present on the surface of the liquid. And we know that evaporation happens from the surface. So let us say that this is the B molecules, right? B molecules can also enter the vapor. A molecules can also enter the vapor. A will form a vapor pressure PA, B will form a vapor pressure PB, and we know that P, that is the total pressure above the liquid, is PA plus PB. Yes, this is how we get the total pressure above the liquid. And we have seen that PA is equal to PA naught into XA and PB is equal to PB naught into XB, right? Both the things we have seen. You know that evaporation occurs only from the surface. So vapor pressure is because of molecules from the surface of the solution getting into the vapor. Clear? So we want to find out what is the vapor phase mole fraction. What is the mole fraction of A in the vapor? What is the mole fraction of B in the vapor? Right? You know that here they are XA and XB. Clear? So the mole fractions in the liquids are XA and XB, whereas mole fractions in the gas are YA and YB. That YA is equal to the vapor pressure of A, that is a partial vapor pressure of A, by the total vapor pressure. That PA is nothing but P naught A into XA. This P total is P naught A XA plus P naught B XB, correct? Similarly, you will write for the YB, right? Which we can write as what? PB naught XB by PA naught XA plus PB naught XB. So the partial pressure is total pressure multiplied by mole fraction. That is what is this? Vapor phase, because Dalton's law will apply for gases. So this is now a gas now. Vapor, any vapor is a gas, right? So the gaseous mole fraction, right, multiplied by the total pressure is a partial pressure, which Dalton wrote like this. Same thing it is now here. So this is the mole fraction in the vapor phase. So that should be Pi by P, which is nothing but Pa by P total. Clear? So this is how we get Ya and Yb for the two liquids which have formed their vapors, and their vapor mole fractions, vapor phase mole fractions are these, right? So they are directly obtained from the Dalton's law. I hope this is clear. Yes. So questions will come on calculation of vapor phase mole fractions. Once the liquid phase mole fractions are given, so you know that XA is known, PA naught is given, PB naught is given, we can find out YA. Clear? I'll give you some time, right? Check if you have understood or there are any doubts to be asked. You can do that. Next, what are ideal solutions? Ideal solutions are the ones which obey Raoult's law at all concentrations and all temperatures. So an ideal solution, suppose you have A as a solvent and B as a solute. So if A interaction and B interaction are same as AB interaction, then it is an ideal solution. Ideal solution has got uniformity of forces. That is, the forces are all uniform. So it is as if that if I remove this A and replace this A with B and make AB, there is no difference. A doesn't find any discomfort when a neighboring A is being replaced by B. It doesn't find any difference because all the forces are the same. So whether it is A interacting with A or A interacting with B or B interacting with B or B interacting with A, there is no difference. So uniformity of forces is what makes an ideal solution. An ideal gas has no intermolecular forces. Keep in mind, ideal gas has no intermolecular forces, whereas an ideal solution will have forces which are uniform. That is the difference between an ideal gas and an ideal solution. Clear? Now, these A and B molecules need to be similar in order to make an ideal solution, because intermolecular forces depends on the similarity of molecules if you have to make uniformity of forces. So take benzene and toluene, right? Very similar. They are very similar to each other. Benzene is a benzene ring. Toluene is a methyl group attached to the benzene ring. N-hexane and N-heptane, a 6-carbon straight chain and a 7-carbon straight chain. Not much of a difference. A bromoethane and an iodoethane, because bromine and iodine are both halogens. Methanol and ethanol, CH3OH, CH3CH2OH. Similarly, chlorobenzene and bromobenzene, or ethylene dibromide or propylene dibromide. So not much difference is there. We are not saying that they are identical. Identical, it will not happen. Even if you have taken C6H6 and a C6H5 deuterium, still there will be a difference. This is almost like, we can call it ideal, but still there is a deuterium which is different from hydrogen. Even there, when you find a difference, you can find more difference between benzene and toluene. But then They are all within the experimental, what shall we say, agreements. So we are thinking that when benzene is there along with benzene, or you have replaced one benzene with a toluene, benzene doesn't find any discomfort, or there is no difference between benzene interacting with benzene or benzene interacting with toluene or toluene interacting with toluene for that matter. So that is how we come to ideal solutions. We are not saying that there will be identical forces. There will be uniformity of forces. Similar there will be. They will not be identical. I hope this is clear. Yes. Next, if you have taken an ideal solution, what are all the characteristics that we can think of? We said it should obey the Raoult's law. It will. So Raoult's law is obeyed. Then when we said that molecule to molecule, A to B or A to A or B to B, there is not much difference. Then it means that there is no heat given out or taken in. There is no liberation of heat or absorption of heat, because absorption or liberation will happen only when there is a difference in the intermolecular forces. If the molecules are not finding comfort staying with each other, right, then they'll absorb energy. Or if the molecules are finding more attraction, then energy will be released. You know that exothermicity happens because of attraction, endothermicity because of repulsion, right? And because there is no attraction or repulsion, there is no difference. Delta H of mixing is zero. That is enthalpy of mixing. That is, while mixing happens, there is no heat liberated, there is no heat absorbed. Similarly, if you have 100 ml of A and 100 ml of B, you will get 200 ml of A plus B. Volumes need not be additive. Mass is additive. For example, 100 grams of A and 100 grams of B will definitely be 200 grams of A plus B, because there is a conservation of mass, but there is no conservation of volume, right? You may see that a few liquids can get into each other, right, with a shrinkage of volume also. 100 and 100 may not give 200, it may give only 190, possible. Or it may increase to 210, also possible, right? But an ideal solution will not do that. Delta V, volume of mixing, is zero. There is no shrinkage, there is no swelling. Here, there is no change in the volume, no heat liberated or absorbed, and obeying of the Raoult's law. And all these things are possible because there is a uniformity of forces. Because this fourth point happened, you can take it as fourth point. Because fourth point has happened, 2 has happened, 3 has happened, 1 has also happened. So ultimately the cause for 1, 2, 3 is 4. The interactions being similar will not give any heat out or heat in, no change in volume, no decrease, no increase, and it will obey Raoult's law. There will be no deviation from the Raoult's law, right? So we have taken up this Raoult's law, but we are not in a position to continue further because we are coming close to 1 hour of our session. 1 or 2 minutes on this. Non-ideal solutions are the ones which do not obey Raoult's law. Now, you could have a positive deviation from the ideal behavior or a negative deviation from the ideal behavior. So what does this mean? That A forces and B forces can be stronger than AB or weaker than AB, right? This is what is the basis for the presence of a non-ideal solution. Non-ideal solution will not have equality of forces. There is no uniformity of force, right? So this is something which we find happens in almost all solutions, because all solutions are non-ideal. They are not ideal solutions because molecules are not identical. They will not be very close to each other unless there are isotopes. For example, as we mentioned, hydrogen replaced by a deuterium, or a C12 replaced with a C13 or a C14. There you might find almost similar molecules I mean, almost similar molecular forces, intermolecular forces. But then when you have a benzene and toluene, right, you know that there is going to be difference, right? But all so less that you can treat them as ideal. Clear? So we have found that most of the real solutions are actually non-ideal, where there is no uniformity of forces. So with this, we have come to an end of this session, because the session cannot go beyond a particular time. So we had to limit ourselves. In the next session, we'll be continuing from where we ended. So take it that this is the first session on solutions, and there is one more forthcoming session on solutions. So I'll wait for another 2 minutes, right, to check if you have got any questions to ask, right? You can feel free to put your questions in the chat box. I'll answer them and see to it that your doubts are clarified. So I'll wait for another minute, right, in the hope that your questions will come up and I'll get an opportunity to answer them. Or if you have already got good amount of clarity, right, it's good enough. The chapter is not very, or the parts of this chapter were not so complex as to require, right, another helping. I think with this, it should be sufficiently an understandable one. And more questions, we'll take it up in the next session so that our, what shall we say, knowledge can get tested at various levels. So it's time for me to say goodbye. Thank you. So see to it that what all things you have read, right, are again brought back to memory. You can watch also this in the YouTube and make yourself more comfortable with the knowledge part. Thank you.